So we have a problem here where something is being auctioned and it's decreasing exponentially by 10% every day that it remains unsold. So the price painting is initially 9,500. What's the price after 11 days? How long will it take to sell if its actual value is $6,000? Okay, so there's two parts to this. So what's the price after 11 days? Well, we need to know the geometric decay. So we need to know the A value, or T1. We know that's $9,500. And we need to know our common ratio. So if I'm losing 10%, I'm going to multiply by 90% every day. So that our ratio being less than 1 is going to decrease every single step. Okay, so I can start writing out my sequence here. It's going to be 9,500, and I can go time 9,500 times 0.9. So I get 85,850. I get 7,695, and then I can keep going, okay, and I can see when it hits $6,000. Okay, so I get 6,925.5, and then 6,232.95, and the next step actually drops me below 6,000. So I know it must have happened somewhere in here. Okay, now if this is a discrete problem, then it wouldn't sell for, actually I'm going to round that to 66. So it wouldn't sell for exactly 6,000. But if we think of this as a continuous problem, it's going to be somewhere between these two terms. So first term, second term, third term, fourth term, fifth term. Somewhere between the fifth and sixth term, we're going to sell for $6,000. Okay. Now we can solve this. This is solving for n, so we can actually still solve this. We could use logs to solve this. We need to set up the general equation. So Tn equals 9,500 times 0.9 to n minus 1. I know my end value is 6,000. And then I can use my logs to solve this. Now logs will allow me to get a non-discrete n value. Okay, so we can actually figure out exactly where in between. We've kind of already solved the problem. We already know it's between 5 and 6. Okay, but let's use logs to kind of zero in a little bit more on that. So I'm going to divide here, 6,000 over 9,500 equals 0.90 to the n minus 1. I'm going to write it as log 0.90 of 6,000. I'm just going to round that to 60 over 95. Okay, get rid of those extra zeros. And it equals n minus 1. I don't have a base. These are not related bases, so I'm going to put this into base 10. So 60 over 95. Use change the base formula. 0.90 equals n minus 1. Okay, so n minus 1, punching into my calculator, I get log 60 divided by 95 divided by log 0.9. I get 4.36. Okay, so then solving for n equals 5.36 is what we predicted. Somewhere between 5 and 6 is where we're going to get our $6,000. Okay, so as a discrete problem, we would probably say n equals 5. If it said at least $6,000, if it said less than $6,000, we would say n equals 6. Okay, so if this kept on going, sold and left unsold, what would it eventually be worth? So we're losing 10% every day. It will never really go down to 0, but what's it actually worth? Well, if I plot this graph, there's my 9,500, and it's going to be an exponential decay. And it's going to decay like this. So although it never will hit 0, because 10% of something is always something and not 0, it's eventually going to be worth less than a penny anyways, and then it becomes fraction of a penny, and eventually, it's hard to say, but we can use a limit to do this. Okay, so although it's never really equal to zero, we can just say the limit as n goes to infinity of our Tn, it goes to zero. Okay, so this is introducing you to this aspect of limits, and this is used in calculus. Although it never really goes to zero, we can just say, well, let's just say it went forever. Although we can't actually go, there's no such thing as forever. If we could, it would tend towards zero, which is true. So this is this idea of this what we call an infinite series. If we let this thing go infinitely, yeah, it'll basically be worth nothing. Okay? And we're going to look at these infinite series a little bit later on.